Okay, we are back with part 2 of fixing the Maplin synth. I wasn't sure how this was going to go down, but there's been a really nice response to the last video. I'm glad some of you found it useful, or at least entertaining. Quite amazingly, there were multiple, I think 3 or 4 people who mentioned the Maplin store in Southend and how they used to go in there and see this thing and lust over it. So yeah, the Maplin store in Southend, quite an inspiration to budding synth builders. I'm going to start this video by saying a few things that I neglected to say at the start of the last one. First off is that I'm not an expert at this kind of thing. I do the occasional repair job, but I'd be hesitant to call myself a professional repairman. I'm learning stuff as I go along, and that is absolutely fine. The barrier to entry with this kind of stuff should not be that you have to know everything about synthesizer electronics to get started. You would never start, and these machines are designed for making music, right? They're not medical equipment that people are depending on their life for. So it's art, not science. Some people said I should have looked at the power supply. You're absolutely right. That's the first port of call whenever fixing something like this, is to check the power supply is all right. It might have been why we had all of those ICs gone wrong, something with the power supply. Sam, before he handed this over to me, had actually already looked at the power supply, replaced a couple of the capacitors and stuff, so I knew that was all right. I just forgot to tell you, sorry. So we left off last time having fixed all of these oscillator voices, and we were calibrating them, and we were going to calibrate them so that they play in tune with the keyboard, but we need to look now at the keyboard itself. Right, so we're listening to oscillator number 1. I should be able to patch the keyboard into it. Okay, that's not doing anything. I think I got this right. Yeah, that's the outputs going to the inputs. Not doing nothing. This is the PCB that is responsible for all the signals coming from the keyboard controller. If you remember last time, we found this loose wire. I forgot about that, so we're going to reconnect that. Maybe that's our problem. Interestingly, when you do patch it in, there is, you can hear there, a voltage coming out of the keyboard controller, not being changed by the keys, but there is something being output, and that reminds me of some of the problems we were having earlier with those operational amplifiers that bust. They just latched to one steady DC voltage. Maybe that's what's happening here, and there's actually 2 outputs from the keyboard. There's a direct and mod. This is the whole schematic for the keyboard controller. This is like a modulated version of the keys. Here we've got the direct output and the mod, and since I'm also getting the same thing from the mod output, if I'm tracing the op amps that we're looking at back through the circuit, I know that the problem is likely before these 2, because they're both experiencing the problem. And also, if we listen to down here, nothing is happening. So maybe the problem is after these, but before those output op amps. And since the sweep knob here, which is just a voltage divider, is here, that makes me think we're looking at IC10 between the 2 of them. If we change the sweep knob on here, which is this voltage divider here, that should be getting summed with what's coming out of the keyboard CV, and that should be represented on the output of IC10. So if I take a reading from the output and the input, compare them, change this, and then compare them again, we'll see if IC10 is potentially the problem. Well, yeah, that is definitely a problem there. This is changing and this is not. But I just got distracted because I measured what's coming out of the output of this op amp, which is coming across here and feeding into this one also. And yeah, nothing coming out of there either. So I'm gonna chase it back further upstream first before I deal with this. Potentially a couple of problems. So I'm trying now to confine it to a specific area. I'm actually starting to suspect the sample and hold circuit around here. If that wasn't working properly, then it would be stuck on a voltage. But over here we have actually this set of switches here are the keys on the keyboard. These are the switches that are made when you press the keys down, and when you press the key it controls an IC that is a solid state switch. You can see the symbol for them here, and those are connected to taps off of resistor ladders. There's two ladders, one big one here and one little one there. We had a resistor ladder in the previous video in the sine wave shaping circuit, if you remember that. And in this ladder here, you've got 12 taps off of it, and those 12 increasing increments in voltage that you're getting off this ladder correspond to the 12 keys in an octave. And you notice we got a load of op-amp buffers around this area of the circuitry. It's just a unity gain non-inverting configuration of these operational amplifiers, and they're there to kind of isolate these resistor dividers from the rest of the circuitry, so they're not being influenced by anything else going on. So nothing on either side of these op amps is gonna, you know, influence the impedance relationship within these. After all of this, let's see if on the output of IC8, when I play the keyboard, if anything happens. 8 pin 6 right there. Well, hey, something's happening. Okay, so I don't know if it's correct, but there is a changing output coming out of IC8. It should be reflected on the overall output. We have tracked down the problem to either the sample and hold circuitry or what is triggering the sample and hold circuitry. Getting closer, so I'm going to work out whether the trigger output is working, which should happen when you press a key. It's just going to give you an on and off signal, which goes to other places in the circuitry, but also makes the sample and hold sample and then hold. I could do that pretty simply because we have a trigger out here on our patch. So if I patch it in to the oscillator, yeah, so we're getting a trigger out at least at this point. So that's again pointing towards more of the sample and hold circuitry not working. I'm not going to go super in depth into the sample and hold circuit. It's a bit complicated, but I can show you the basics. The main part of it is formed by two components. There's a switch, which is Q8 and Q7 in the two stages of this sample and hold circuit. That's a transistor switch, and the other circuit components are these capacitors, C9 and C21. This one's drawn out a bit easier for you to understand, so I'll use this as an example. The signal flows through the transistor when it's turned on by the trigger signal that we were just listening to. That happens when you press a key on the keyboard. That lets the signal come through to the input of this buffer here, okay, and the capacitor is connected between that signal and ground, and when the signal passes through here, the capacitor is going to charge up to the value of that signal once this switch opens again and effectively disconnects this side of the circuit from all of this, and this buffer here disconnects in essence the circuit from the rest of the circuit around here, just like how the resistor networks here are between the buffers. That kind of like isolates it from the rest of the circuitry. You can think this capacitor here is just kind of stuck there on its own with nowhere for this this current that is accumulated to flow to. There's no current path, so it just retains that there, and then the op-amp buffer reproduces that on the other side of it, and so it's a very, very, very simple memory device. It just remembers the analog voltage level that is put here. Okay, and interestingly, you see you've got the variable resistor, the glide control here, which that's a Portamento. It's just how quickly the change is made between two different notes. So whether it will go do D or do do. Okay, this is a sliding between them. There's an RC relationship, resistor capacitor relationship, and that controls the timing, how quick the capacitor charges up or discharges to the signal level. That is just adjusting that resistor capacitor RC time constant relationship. So a sample and hold circuit is essentially the same as a Portamento circuit. Interesting. My attention is now being drawn to this IC16, which is controlling these transistor switches. That is a 4001 NOR gate logic chip. Before, with the oscillators, we were looking at astable circuits, so that's that they're not happy existing in either state, on or off, so they keep oscillating between the two of them. Well, this is a monostable circuit, so it's happy staying in one state, but then once the trigger comes in and changes it to the other state, after a length of time set by these, it will revert itself back to the original state and stay there. It's happy in that state, monostable. You can also have bistable circuitry, so after you trigger it to flip into one state, it will stay there, and then if you trigger it to flip into the other state again, it will be stable and stay there until you do it again, if you see what I mean, but won't do it on its own. And the reason why you want a monostable circuit here is just so that you can ensure that whatever length trigger you're getting in, you are getting the right length of control signal to control these switches. So there's circuitry within here to set the amount of time that this circuit is going to be in its unstable state, if you see what I mean, and then revert back. Well, I just plucked this out, and very interestingly, it's actually a 4016, not a 4001, as it should be. 4016 is an analog switch, not a NOR gate. So, well, that may have been the problem. I don't know how that got in there. That's very odd. Okay, I've put the NOR gate in there where it should have been. I'll trace the signal further. It's coming through this switch when you press the key, coming to the other side of IC17, is coming down to this side of the transistor, but when you press the key, nothing is happening the other side of this Q7. Now, I did see this earlier, and I should have taken it more seriously, because there's already a repair in here. Can you see that? Let me get some light in. You see that transistor there that has been soldered in. That is Q7. So I think that might be the issue. I'm going to replace it and see what happens. I only had a 2N3819, which is the same type N channel JFET, but with a different pin out. So I had to cross the legs over a little bit, but it's all right, it'll work. Yes, so we have a result. We are measuring what we should expect out of IC9 now. Q7 is working, but back to the old problem. I think IC10 definitely then is bust, because when I'm seeing the change in output here, the output of this one is not changing. So I think we're going to have to swap out IC10. Hey, moment of truth. Turn this up. Oh, yes. Okay, cool. Right. Obviously not tracking correctly, but big improvement. So we got all of the octaves working, but now let's try the individual notes. Hey. Okay, so the F has a problem. All the Fs have a problem. It didn't change note there, but the rest of them are alright. Okay, so that means that the F is not sending a signal to this sample and hold circuit that we just looked at to open these transistors. Yes, that's it. The F is not sending out a trigger, which means that the sample and hold is not allowing to change the notes. Okay, so we got to follow down where all the triggers are. Okay, so you see how all of the notes within the octaves, they're all joined together and then go down to their switches. Here you see the numbers here correspond to the control pins on these switches. That's how the CV is selected, but also all of the notes in all the octaves, they're all also connected together to go through to the trigger circuitry. They go through these resistors here and then down here. We know, because all the triggers are working for the other notes, that everything from this point going over here, that's all working. It's the connection between the F keys and this point. There's a broken wire, and this ribbon here is what's coming from the keyboard, and I think all of these connections are good. We did look at them earlier when I reconnected this white wire. I'll have another check. So that might mean that the problem is on the other end, down on the actual keyboard, or maybe one of these resistors is soldered badly. Let's have a look. We have found the problem. It's the other end of that white wire off the ribbon cable is disconnected. Both ends were disconnected. Oh dear. Very fortunate for us, the F is actually the bottom key, which means that that wire connects on to that solder joint. Can you see there where it's just dangling off? So we can get to it. We'd have to dismantle a load of stuff, which is fortunate. Right, so we are at the hardest part of this restoration, I reckon, because it's all to do with pitch, and any errors with pitch are very noticeable. This era of synthesizer, the tools they had available and stuff, and the way it's done, is not famed for being completely stable and in tune, and to some degree people kind of like that. The imperfections in these things are actually what make them a bit special sometimes, to a degree. And so, like, if you look at like the Prophet 5, that was slightly unstable with its oscillators, and when they did the Prophet 6, which was like a kind of updated idea of it, they actually included a slop knob which imitated that out of tuneness a bit. So there's a middle ground where it's musical but not annoying, and at the moment this keyboard is annoying. And I've done quite a lot of tuning different trimmers and stuff, and we are not there. So I'm going to have to dive deeper into the circuit, really analyze it, and figure out where things are going wrong. Now, it's worth rehashing at this point how humans perceive pitch. We hear pitch exponentially. So that means that as the amount of vibrations per second doubles, we perceive that as an octave. So say you've got a C here, right? The C above it is oscillating twice as many times per second as this C. And then this C above this one is oscillating twice as many times as this one. So in fact, it's oscillating 4 times as many as this one. The logarithmic way that humans perceive pitch is kind of like nature's compression. Because could you imagine if we experienced pitch linearly? The range of sounds that we would have to process in our brain would be huge. So the kind of compressing that sensory information into like a logarithmic way is just makes things in nature much easier to comprehend. Well done, evolution. So nowadays most synthesizers use a system for control voltages of 1 volt per octave. This older way of doing things tracks the voltage with the hertz, so hertz per volt is the older system. And the reason why they used to do it like that in these days is because for a volt per octave linear CV system, you need complex exponential converters and things, and in the old days that was quite unstable. So with the technology they had, it made sense to do the hertz per volt system, but has its own problems and drawbacks as well. As it is, I've set a load of the trimmers in here. You can see in there, those are the trimmers for the notes within an octave, and then you've got more trimmers over here for the octaves themselves. I have set those so that when I measure on the multimeter, I'm getting the right exponential voltages being sent out over each octave. So it's not this, but you can imagine that each E is 1 volt, 2 volts, 4 volts, 8 volts. So when I play that, put that into the oscillator, I should be getting those octaves in tune as I expect, but I'm not. So that tells me that somewhere between the voltage levels that I've set on those trimmers and the integrator within our oscillator, something is getting scaled wrong. As I've worked out on this piece of paper, it ain't simple. So what I've done, and not for every pitch because I don't need to at this stage, but I've started charting out the voltages that I should expect from the keyboard, and then I'm probing around the circuit to see what we're actually getting, and then I'm going to figure out what I can do to fix that. And we briefly went over this section of the circuit earlier, but let's look at it in more detail. This is the resistor ladder here that we're tapping off with the switches, which are operated by the keys of the keyboard. And you can adjust the trimmers, which is this symbol here, the resistor symbol with a arrow pointing to it. There's little trim pots inside. That's these ones here. You actually can adjust with your thumb, and the F is adjustable by this one here, and you need to do that one first because that is here and that affects all of the rest of them up here. But apart from that, adjusting these doesn't affect any of the others because you see they're kind of all in series, and you're just adjusting the points that these branches are tapping off in the resistor ladder. So this is setting all of your control voltages within 1 octave, and the top E here is just set. This switch goes on, and so this voltage point coming out of the op amp here is the E, and the tune can shift that. That's this one here, so I've set that to 0, and we've got the top E there. So if I just go off of that and then come through here, the next kind of stage with this next resistor ladder, which is kind of isolated from the other one and the circuit after it by these buffers, these op amp buffers. What we're doing here is taking the voltage off of this ladder and through these switches, dividing it so that we can get octaves down. So if we're playing in the top octave here, this switch will be on and we'll be listening to the direct output of the op amp. So none of this is getting divided down. If we play in the octave below that, this switch is on, and we've got a trimmer here so that we can divide the voltage coming out of the buffer in half, so we get half the pitch. And then if you play down another octave, you got this switch on, and so we're listening at this point here to this tap off of the ladder, which is dividing the original voltage by 4 and then dividing it by 8, and so we're getting the octaves going down. Fairly simple, really. And I've probed around the circuit, and so I know that all of this is working right. We're getting what we should expect out of this point. It's as we're going down here that things are starting to vary in strange ways. This operational amplifier here is not an op amp like we've been seeing before in a plastic dual inline package like these ones. It's actually this one, which is in a can, and it's being weird. So with a top E, we should be getting 4.95 and volts, and we're getting that up until this point. But after this op amp, it's dropping it to 4.73, and that might be fine if it was doing it equivalently with everything else. But very weirdly, the second octave down is getting scaled differently to the other octaves. I don't know why. It's weird, and it's not like, you know, an offset. It's weirdly attenuating, but not not in a uniform way. But just turns out that that operational amplifier has the same pin out as a TLO71, and so I'm gonna swap it out for one of those. And seeing as it is a buffer configuration, we should get a representation of exactly what is coming in on the output, and then we can move on and make sure that these two stages are also not amplifying or attenuating anything either, and then it should just go to our oscillator, and then we've got to work through the oscillator then. But there is some scaling that you can do on the oscillator on the panel to help tune out any errors, and you know, temperature drift and all that stuff comes into all this. But so I'm just trying to minimize all of that, and we're going to have to look at all the resistors here, because ideally these inverting amplifiers are doing the same kind of thing as the buffer. They should be outputting, well, adding these things together, but not amplifying or attenuating, just adding them together. And that's to do with the relationship of these resistor networks. So I think I'm going to have to go through and match resistors. I think that's going to be the simplest way to ensure that we're getting what we want on the output. And people did mention in the last video that the 7.4 ones that I replaced the LM301s with, not the best op amp, and I wholeheartedly agree, but they were the only thing I had in stock. The reason why is because I don't use them, so they were left. So I've now got some TLO71s, and because we put them in sockets last time, I can swap them out. You can see from the diagram here that the holes in the PCB are actually just like a dual inline package, so it shouldn't be too difficult to put one in. I'm just going to need a jumper between this point and there. I think the reason why they used this originally and not just another LM301 is because it has an especially high input impedance, so that's good for the sample and hold circuit, but TLO71 will do the job just fine. There you are, there's an op amp in its socket there instead of the can enclosure, and it's working so much better now. We're actually getting the 4.95 represented exactly on its output now, and as I change it, it's following it as it should. It's a voltage follower. So the next step is looking at these two op amps here and trying to get the outputs to exactly match the inputs, so to do that we need to balance these two resistors here, because the inverting operational amplifier is feeding back through this loop to this point to try and counteract exactly what is being summed at the node here between these two resistors. They have a relationship, so 10k and 33k, so the 10k is going to have more influence on this, and that's being fed by this, but I've set the sweep pot down here to the midpoint, and if you remember last time we were talking about diodes in the sine circuit. One thing I neglected to tell you, a little detail about diodes, is that they have a forward voltage, and that means that they will only start conducting after the voltage rises above that threshold. In this case, it's going to be around about 0.7 volts, so there's a little dead spot here where current can't flow in either direction unless it goes over 0.7 plus or minus 0.7 volts. So I've set the pot here so that effectively all of this is out of the circuit, it's disconnected, it's in the little dead spot here, and so now we are only getting represented on the output the voltage coming in here, and the amplification factor determined by the balance of these two resistors here. And if they're exactly the same, we should get an amplification of 1, which is unity. So it's effectively an inverting buffer, just like this, but flipping the polarity of the input signal. And then it comes through, and we're going to do a similar type thing with these 33k resistors. There's a little circuit here which is acting as an offset, just to offset the offsets of the operational amplifiers themselves, the little errors that they can introduce. Now you'll see there's a 10 mega ohm resistor there, which is a lot more than 33, so this little network here is not going to have that much influence on the voltage summed at this point. So to get these resistors matching, I'm going to go through a whole load of them with my multimeter and check that they're exactly the same, because if you don't know, resistors, even though they say that they are a specific ohmage, is that the right term? They're within the tolerance, and so these particular quarter watt resistors that I have here are 1% tolerance, so they're actually going to be plus or minus 1% of 33,000 ohms. So I need to go through the multimeter and check and find two that are exactly the same. I hope you're seeing in all this circuitry that once you understand the simple concepts like voltage dividers, it applies to so many bits of this circuit, and all you need to do is just build up a few of those basic building blocks, like knowing your operational amplifier configurations, and soon enough, almost like a modular synth, you can add together all these little modules and then get an overview of how the whole circuit works. So overwhelming big thing, break it down into tiny parts, and then you can put them all together, and it's not so bad to understand it. So these are a couple of them. This one was 32 and this one was 33, so quite a bit different. And you might be saying to yourself, well, why don't you just adjust the difference in the tuning on the oscillator to compensate for this? Well, unfortunately, the difference is so much that the range of the scaling pot on the oscillator is not enough. And I'm not showing a lot of the annoying things that I'm doing in between these stages, like these wires keep breaking off and they're driving me crazy. But apart from that, it seems to be going quite well. That was not easy to do. A load of calibration. You have to go over it multiple times to hone in exactly. That involves these things that we haven't talked about yet. These big trimmers on the octave switch. They're not so bad as they look, but it did trip me up once when two of them were touching, and I was like, why is this happening? And they was just shorting together and doing something weird. So I've learnt that now. So when that particular issue happens, it's because two of those are touching. I didn't film a lot of that process just because it was so involved. It may have seemed like I just came straight to the conclusion of how to fix it, but it took a little while to think over what could possibly be going wrong. Oh dear. Okay, the sample and hold. Here's an interesting thing that, if you think about, is a potential problem with the hertz per volt control voltage scheme versus the volt per octave. As you're going stepping up voltage levels exponentially, the glide, the portamento, is gonna take longer to glide from here to here than from this C to this C, and that's because you're stepping up here twice the voltage range that you are here. So obviously it's going to take longer to glide for the same position on this knob, and there's actually resistance across the transistor in the sample and hold circuit. So there effectively is a resistance in this circuit the whole time, and so you'll hear here, even with the portamento off, the difference between the time it takes to go between those notes and these two. Can you hear it's like sliding up? And that's much more immediate. So in the top octave, it does actually take a little bit of time to glide up, and a couple of times when I played it fast, you're not holding down the key long enough for it to actually reach the note. Slightly flat, isn't it? If you hold the note down longer, then it reaches it. Flat. Yeah, so I mean, different type of FET transistor, possibly have a less like resistance across it. I'll have to swap that out. Other than that, there is no other resistance in that circuit, in that point from here to here, so it has to be the transistor. So maybe I'll swap that out for another one. I'll do some research of what could be a better type, because that is slightly annoying that it's not quite in tune. Onwards, so let's check now the noise circuit. You access the noise through this switch here, which is part of oscillator 4. So you can choose to have sent to the mixers here on these knobs. You can choose to have another output from oscillator 4. So let's turn this this one here. So you can have the sine from oscillator 4. You can have the what's that one? The triangle and the square. You can also then select the noise, and doesn't sound very noisy to me. I'm just getting clicks. Oh dear. Another thing broken. Quite a fun little circuit, the noise one. It's digitally made, the noise, which means that using the shift register and logic gate here, you're sending out a stream of pseudo-random on and off binary signals that kind of approximate the kind of random noise that you get in like a white noise or a pink noise signal. That you can kind of filter it. Here, this is a filter circuit to kind of change between an approximation of white and pink noise. So this shift register here is just a kind of a load of units that can either be on or off, and they pass their state to the next one in the sequence on the clock, which is generated here by this NOR gate that has a load of feedback and stuff and generates about a 32 kilohertz clock that gets fed into here, and so the units within the shift register pass along their data state, and there's certain taps off of this that go through and get fed back into previous states, so it's kind of pseudo randomly generates a long string of gobbledygook, basically, of on and off signals that is random enough and doesn't repeat enough for us to convince our ears that it's just random noise. The issue, we're hearing the clicking, so I immediately thought, well, it's not being clocked fast enough to be sending out this kind of pseudo-random noise signal at a kind of frequency bandwidth that will approximate the noise. You're just hearing it as clicks, like when you turn an oscillator all the way down. So I was looking at the clock circuit, which is NOR gate, and we can just do a little trick. I don't know how people will feel about this trick, but sometimes you could just use your fingers, because your fingers have a certain amount of resistance. So if you touch parts of the circuit, you're not going to short them, but you can kind of connect them as if you were connecting resistors across and stuff. So I just kind of touched the back of the back of where the IC is soldered into. There you go. And so I think there's a faulty unit on one of these within the NOR gate, and if I bypass it with my finger, then you're getting the clock or something like that. But something's wrong with the NOR gate. Oh, new chip in there, and we have noise. Oh yeah, and you can hear the difference in the filter circuit. Right, okay, so the other section over here is the controller, which is just an offset. So you can send a signal into it and scale that with this knob, and then you can mix it with a DC offset, which is set by this knob. So if we listen to this oscillator, there you go, and then on the patch bay, we send the controller into the pitch CV of the oscillator. When we change these knobs, we should get a changing pitch. Just get in the steady pitch. So that means that the output of the controller is stuck, is latched. So that's pointing towards this op amp being burst. It's quite a simple circuit here. It's just mixing these two inputs through here, an inverting amplifier, and then inverting it again to get the same polarity as the input, if you see what I mean. Well, I'm measuring the voltage on the output of these two op amp stages here, and I'm seeing that on the first stage we have minus 12 volts there, which should never happen because there's nothing going into the input at the moment, and the offset level can only go between plus 5 volts and ground, so you shouldn't be getting anything outside of that range on the output. You can see the op amp's powered by plus minus 14 volts. It's not a rail to rail op amp, so for it to be latched at its rail at 12 volts is about right, what you would expect. So and then IC6 is mirroring it inverted in polarity. So I think IC6 is fine. IC5 is the one that's bust and latched to its negative voltage range. Okay, let's fixed it. Now if we patch oscillator 2 into the controller input, we can use it like a vibrato to control the pitch of oscillator 1, and then the offset just moves the center around. So you mix in oscillator 2. There you go. Well, let's take a look at the joystick and see if that is working. And in the vertical direction. How many times must a man solder these bloody wires back onto this thing before they call him a repairman? Okay, so we have fixed the oscillators section, we have fixed the noise, we have fixed the controller, we have fixed all of the different keyboard controls and all the keys themselves, along with many broken wires to keep breaking. The joystick is working, so we've got everything. All the mixers are checked. Some scratchy pops, but we'll sort them in a bit. So everything up to here, all good. And I'll give you a little snippet of me playing with it as it is right now. It sounds pretty cool. I'm guessing if you've watched to this point in the video, you've quite enjoyed going over all the electronics inside of this. And if you want more of that kind of stuff, then we need your support, to be honest, because it takes a lot of effort to put videos like this together. So if you want to give us a one-off donation maybe to the museum, you can do that on YouTube Super Thanks, or you can buy us a coffee. There's links to that in the bio, or PayPal on the website, or you can subscribe to the Patreon, where you get exclusive stuff in return for your subscription, or you can come and visit us at the museum, buy some merch maybe, and it all helps to support what we're trying to do, to share all this stuff with you, because this is the ultimate aim. Is this is going to go in the museum so that you can actually play with it, which is pretty cool. So all those people that visited the Maplin store in Southend back in the day and dreamed of playing this, you can come to the museum and play it. There's also a link down below to my channel where I do some more stuff like this, silly videos, but also videos about synthesizer design and stuff. So if that's your bag, you may want to check that out. Do let me know what you liked or disliked about this video, and whether you want a third part looking over the rest of the circuits that are left to fix. That's the envelope control, the filter and stuff. We like hearing your stories and things that you've got to add to the videos, so please do leave a comment down below. All that liking and subscribing and stuff does help with the YouTube engagement, which is great. So let's add in the oscillator number 1. Oscillator number 2. Oscillator number 3. Oscillator number 4. Got the sync on. Pretty good, I reckon.